I came up with the idea for a translator when I met a French girl. That's really where the story starts. I was on vacation and I met this girl. It was difficult for us to communicate because she didn't speak English very well. And even when we tried to find a solution, like using some translation app to communicate, it's horrible. Look, if you and I are speaking and our phones are in our face like this, forget it. This is a wall. We're out of this real world interaction. But this in your ear puts us right back in it. Elodie, put this in your ear.
Je mets ça dans mon oreille?
Yeah, put it in your ear.
Comme ça?
Yeah.
Okay.
Can you hear me in French?
Pouvez-vous me entendre en français?
Oui! Et je peux t'entendre parler français? Mais c'est
Yes,
génial.
I can hear you talk French.
Attends, comment ça se fait?
But this is awesome. But how you do it?
Yeah, it's translating. It's translating. This little wearable uses translation technology to allow two people to speak different languages, but still clearly understand each other. Simply put, when one person speaks, the other hears it in their language.
Developing the pilot has been an intensive process. Our team has been working on it for over 2 years. Andrew is our original co-founder and oversees product development. I'm an electrical engineer and expert in manufacturing. We also have a mechanical engineer, software engineer, PhD in machine translation, as well as an industrial designer. Our wide breadth of experts has allowed us to develop a product from the ground up.
We wanted to create something that hugs the curves of the ear without being obtrusive. Something snug but fashionable to wear. In the process, we just decided to throw in an extra earpiece for wireless streaming music. That means the full system includes 2 earpieces and its accompanying app. It's from the app itself where all of the languages are uploaded to the earpiece. It's kind of an end-all solution for the traveler or the international professional. That's what we're doing here at Waverly Labs. It's simply the most advanced communication wearable. This Indiegogo campaign helps us finish what we started. We can get the earpieces along with this portable charger, manufactured and delivered within a year. The app works on its own if you just want to use the app for basic translation. And we'll have the app out by late summer, first for our backers here on Indiegogo. But for the full experience, you really want the earpieces too. It's the dream, you know? A life untethered, free of language barriers. It's just that it's no longer a dream anymore. It's real.
A battery pack in your house and you have an electric car, that's something that scales worldwide, that you can solve the whole energy equation with that. So, yeah. Obviously, next slide, please. So we'd like to introduce the Powerwall 2. This is a big step above the Powerwall 1. It has twice as much energy, more than twice as much power. So it's a 14 kilowatt hour energy storage, 7 kilowatt power output. And just to put that in basic terms, you can take a 4-bedroom house and you can have you can power your fridge, the sockets, and lights for a day. And if you have solar on your house, you can power it indefinitely. So that's just with one. And and then on the utility side, we've got the Power Pack 2, which similarly doubles the energy. So it's a 10 kilowatt hour capability, 50 kilowatt power output. And this can scale to unlimited size. So it's, in fact, we've recently announced the biggest utility battery installation in the world, which is going to be with Southern California Edison. Let's go to the next slide. So we have an 80 megawatt hour battery installation that's being built right now. So, and then we announced one earlier this year, which is for a utility in Hawaii doing 52 megawatt hours. You're going to see a lot more of these announced over time. And I think it's important to make sure people appreciate that the solution is both local power generation and utility power generation. It's not one or the other. Sometimes the solar roof is positioned as a sort of a competitor to utilities, but we're actually going to need utility power to increase, and we're going to need local power generation. Because if you transition all energy to electric, that roughly triples the amount of electricity that's needed. So you need about a third for transport, about a third for heating, and about a third for what we currently use as electricity. So the future is bright for utilities and for local power generation. I would expect it to be roughly a third local power generation, roughly two-thirds utilities. So I think it's a very bright future for utilities and for rooftop.
At IBM, we are conducting research to build a universal quantum computer. And to get there, we are putting our quantum computing capabilities on the cloud and making them available to anyone interested in learning or experimenting with quantum information. Now let's walk through an example of how to use our cloud-enabled quantum computing platform to run a simple but fun quantum algorithm called Grover's search. Now one of the many advantages a quantum computer has over a classical computer is its efficiency for searching databases. Grover's algorithm reflects this capability and provides a quadratic speedup on an unstructured search problem. Now, a good way to appreciate this algorithm is to actually consider a simple card game, like 4-card Monty, where you have 4 standard playing cards, only one of which is a queen. Now, when the queen is hidden and the cards are all shuffled around, it could be in any one of 4 positions. Now, on average, it would take you 2 1/4 tries to find that queen, with only a chance of 1 in 4 of getting it on the first shot. But with a quantum computer, you can run Grover's algorithm. Using 2 of the qubits in our processor, get the right answer on the first and only try. Here's how we run Grover's algorithm through our Composer tool. On the Composer tab, we can see what essentially looks like a music staff, with each line representing one of the qubits in our processor. Although there are 5 qubits that we can use, we're going to focus on just 2 of them for the purposes of this algorithm. I'm going to put in a number of these different gates and construct this entire Grover's algorithm. So now we've got all of the gates that we need to run Grover's search algorithm in the Composer. Let me describe some of these different parts. The first part over here involves making a superposition state of both qubit 1 and qubit 2 using this H gate or Hadamard gate. The second part is what's known as the oracle function. This is equivalent to basically hiding the queen. And what we've selected here is actually a combination of gates that hides the queen in the 4th slot. That's then followed by this quantum inversion step. Now this is a sequence of gates which we would put in for this algorithm regardless of any of the different slots that we would have chosen to hide the queen. The real power of Grover's algorithm sits right here in this inversion step. It takes the entangled space of the 2 qubits and turns it into something that we can measure and understand at the end. And that's done by doing these measurements on both of the qubits right here. We can take this whole algorithm and run it on our actual processor. We can also choose to simulate it with the simulate button on an ideal case, but we'd like to see what happens with a real processor. So we hit run, and what we'd like to see is this real quantum advantage of running this algorithm for finding the queen, and what we'd like to do is just run it once. So we're going to select one shot here. We're going to ask it to run a new execution which sends that code directly to our quantum processor in the lab. After our execution has been run, it goes into the queue in our actual processor, and we wait for the results to come back, and we look for it in My Scores tab. Here in my scores, we can see all the different algorithms which we ran through the Composer tool. And the topmost one here is this Grover search algorithm which we just ran. And we can see that the results are actually in. And so we hit this little bar graph button and find the results. And in this case, what we found is with the single shot of running Grover's algorithm, we found 1-1, corresponding to that fourth slot where we hit the queen. With just a single run of Grover's algorithm, we were able to find the queen. Whereas in the case of classical card playing, it would have taken us 2 1/4 tries to find it.